Good afternoon, everyone. This is Diane Fodell. Thank you for joining the Cognitive Systems Institute speaker series call today. I'm happy to introduce Dan Tecuci, who's a Watson natural language processing engineer. Dan graduated from the University of Texas at Austin with a PhD in artificial intelligence. During that time, he developed a generic episodic memory module and contributed to the development of several large-scale artificial intelligence projects, Project HALO, RKF, and KALO, which was a precursor of Siri. He then moved to Siemens Corporate Research, where he led the development and deployment of a natural language QA system, and where he also developed a prototype system for diagnosing heart diseases from patient data. Dan joined IBM Watson in 2014, where he led the development of Numerati, QA from tables, and then moved on to fixing recipes for IBM Chef Watson. His main areas of expertise are knowledge representation and reasoning, question answering, NLP, and complex knowledge indexing and retrieval, or episodic memory. And that's what he's going to talk to us about today, enhancing intelligent agents with episodic memories. Thank you for being our presenter, Dan. I'll turn the call over to you.
Thank you, Diane. So I'll get right to it. I'm going to start by talking a little bit about the human memory and justifying the need for such an episodic memory in the context of a cognitive system. I'll present our approach to building such a generic episodic memory module, the requirements that we drew, and then a proposed implementation. At the end, I'll have an overview of the evaluations that we've done and have some time for conclusions and discussion. So why do we even need memory? I think that a quote summarizes it best, that those who cannot remember the past are condemned to repeat it. I would, I think uncontroversially affirm that remembering is an essential characteristic of intelligence. And we as humans can recall our past experience and use memories in a lot of ways to solve similar problems, to avoid unwanted behavior, to reason about the world around us, for example, to recognize the plans or the goals of others around us, as well as to remember our own goals and track our progress. So I would say that memory and intelligence go hand in hand. So in a cognitive system, what role does memory play? Well, experience is an important knowledge source. However, current system is mostly unused. And I also say that the importance of this memory system grows with the complexity of the task. So the more complex the task, the greater need for a memory we have. And it also grows with the life expectancy of the system. So as the system is online for a longer period of time, it acquires this experience, and it should be able to use it in the future. Now, of course, there is an approach in machine learning, a tribe, so-called, and I would call it the eager approach, that uses memory and uses it to generalize based on it, and then it discards that particular memory. So, case-based reasoning is an example of that, SVM, another example. And basically, the assumption they make is that all value can be extracted upfront from that example, so there is no need to keep it around. Of course, there is a lazy approach as well, which is store everything for now and use later, do the generalization later, or do the learning part later. And this is the camp that I will be basing myself in for this talk. So what are the benefits of using stored memories? Well, I think the straightforward answer is that having memory can help improve performance. Basically, a system can solve problems faster by adapting previous solutions, so kind of bypassing the need to reason from first principles. It can also improve the competence of the system. So let's think of a system that performs search. Prior experience can provide information on how to conduct this search. So we can reduce the search space based on prior experience. But memory can also help an intelligent system perform additional tasks, like avoiding and detecting failures, so doing prediction or monitoring long-term goals, as well as reflecting on the past. How well have I done at that particular task at that particular moment in time? Can I improve, and how? So I'm going to distinguish between two kinds of human memory, episodic versus semantic. So episodic memory is concrete. It's about personal experience that is dated. So where I parked my car this morning is something that I don't share with a lot of people, right? It's my personal memory, and that's episodic memory. Semantic memory is abstract and timeless in general. So the color of the sky is something that we all share. So there are a lot of similarities between these two kinds of memories. That the knowledge is acquired through the senses. We automatically retain that memory, and then retrieval is again automatic, and it's triggered by external or internal stimuli. So I'm going to focus on the episodic memory. That's the goal of my research here. There's a lot of work done in semantic memory or knowledge bases that has happened before, so I'm not going to go into that. So there are three main functions that an episodic memory needs to implement. One is encoding, deciding when to store an episode, which is called activation, deciding what to store in a particular episode, which is called a salient feature selection, and then cue selection, deciding what features to use as cues in retrieving such an episode from memory. In terms of storage, an episodic memory needs to maintain such an episode in memory. For example, deciding whether to keep it around or forget it at some point. And after encoding and storing an episode, we need to retrieve it. So retrieval is basically has four parts. Queue construction, think of it as the query to be run against memory. What features should we use from the current situation to retrieve the previous memory? Matching, basically query execution, recall, constructing that episode back, and humans also have a recollective experience. We remember that we remembered something. I will address the parts highlighted in green here, but I'm not going to go into recollective experience for the purpose of this talk. So I'll briefly describe now the proposal for our generic episodic memory module, and this was work done in the context of my dissertation. So we started off with desired characteristics, and the main characteristic we wanted was to be able to use the same memory for different applications. So we wanted to kind of break free from this rule that you can use a memory for one particular task. We want it to be a generalization of case-based reasoning. So that's a generic characteristic. We also wanted to separate the memory from the application and give the application access to memory through an API. That would allow us to focus on building the episodic memory module in isolation of a particular application. And we also wanted to be able to store complex experience that is temporal, graph-based representations for such memories. The function that memory implements is basically to return the most relevant prior episodes. So we're going to build a content addressable memory for such episodes. And the advantages of having such a generic memory module is that we can focus on the memory organization itself, as well as reduce the overall complexity of the system because we're doing it in a modular way. The general requirements are accuracy in retrieval. We want to have memories relevant to the situation at hand. We also want memory to be scalable, so to accommodate a large number of episodes without a significant decrease in performance. Humans don't take longer and longer to remember, even though our experience grows as we age. Efficiency, we want to be able to efficiently store and retrieve, both in space and time. Content reducibility, that we should be able to recall a memory by its content and not by some random key that we generate. Flexible matching, that the memory recognizes prior situations even if they only partially match the current situation. So from these requirements, we extracted three main challenges. First is the conceptual representation for a generic event. The second one is the domain-independent storage and retrieval algorithm. And the third one is the building of a flexible interface to expose these memories to an intelligent system. I'll address them in order. The episode is the basic unit of storage for our memory. It captures a complex event with temporal extent. We chose to represent it as a conceptual graph, sets of subject, predicate, object triples, and it uses an ontology in the background for concept representation. We divided episodes into three dimensions. The context, which is the setting in which the episode takes place. The content of the episode is the ordered set of events that happened, and the outcome is some sort of evaluation of the episode. So let me see if I have an example. Yeah, I have an example in the next slide. And we decided to leave the application to determine what constitutes an episode. So we are agnostic to the exact nature of the episode. So if we look at in the planning domain, this was an experiment done a while ago where people were asked to basically translate natural language into Linux scripting commands. So in this example, a person was given the instruction to move all Perl scripts to the Linux folder. And this is the context of such an episode. The content is the actual command that the person issues from the terminal. And the outcome of such an episode is, for example, whether he or she successfully accomplished that command. So now that we have a representation for the episode, how is this representation helping us achieve our goals? So in terms of the episodes being multifunctional, in a planning episode, as we saw, we divided it into three: a plan goal, a set of plan steps, or rather a sequence of plan steps, and a plan outcome. So if we do retrieval on these separate dimensions, we can accomplish several goals. So, for example, if we do retrieval on the context dimension, that is, given a planned goal, show me other plans with similar goals, we can do planning, right? Retrieval based on the content of an episode that is given a set of a sequence of events, show me other episodes with a similar sequence of events, we can do plan recognition, because from the plan steps, we can go back to the prior goals that were accomplished by similar episodes. So we can do plan recognition. But we can also predict the outcome. So we can predict whether an episode is going to be successful or fail. We can also do retrieval on the outcome of such episodes. And basically, we can do things like root cause analysis. What caused the failure of a certain part? We can trace it to the actions that happened before it. So this basically shows how the representation of the episode broken down into context, content, and outcome, and retrieval that happens on either of these three dimensions can use the same episode to accomplish different tasks. So now that we have the episodes broken into three dimensions, how do we store them? We basically store them unchanged in memory, and we do indexing on each dimension so that we are able to do retrieval on each dimension. And we do what we call a shallow indexing. So we basically break up the graphs and generalize them a little bit. And you'll see how this comes into play in the retrieval algorithm. So we do a two-step indexing or two-level indexing. First one is what we call shallow, and the next one we call a deep semantic matching. So in terms of shallow, we compute what we call surface level similarity, with the goal of reducing the pool of potential candidates. It's fast, it has high recall, but low precision. So think of it as a keyword search that Watson question answering pipeline does, or a keyword search in let's say, Google search. The second step is the deep semantic matching. We use a graph matching algorithm, and we use that to score, or rather rank, these retrieved episodes based on how structurally similar they are. It's slower, but it has a much higher precision. It can use taxonomic or ontological knowledge if that is available, transformation rules apply to graphs if they are available, and is able to resolve various mismatches along the way. And the output of this retrieval algorithm is a set of similarities and differences between a given stimuli and a prior episode, and as well as a score. So qualitative and quantitative differences. The API consists of two functions, the store and the retrieve. And as I said, retrieve returns a set of a ranked list of prior episodes, as well as for each of them a match score and how the match stimulus differs from the prior episode. We developed an incremental version for recognizing sequence of events. It's applied to plan recognition as well as dialogue understanding. The idea is to segment the prior episodes based on their temporal links, recognize the individual pieces, then aggregate them into episodes. And the confidence of such a recognized sequence of events is a combination of the individual confidences of the pieces as well as the order in which they're observed. I won't go into the algorithm here, but it's you can find it in the reference section. There's links to various papers. How does this do in the so-called real world? So we evaluated our implementation of this generic memory module on 3 tasks. One was memory-based planning, in which we were given the system an initial state plus a goal, and we wanted it to be able to build a plan to accomplish that goal. A second task was the goal recognition. So we give the system a plan, a sequence of events, and we want to infer what that plan is supposed to accomplish. This is called goal schema recognition. As well as on a third task called memory-based question answering. So we gave the system a question and we wanted the answer back. And we measured task performance in terms of precision and recall, as well as memory performance, retrieval time, and the memory overhead that is added. We use the same representation for memory across these 3 tasks. So no task adaptation was done. I'm going to keep the description of these tasks. You can find them, as I said, in the reference sections and papers. Maybe tell you a little bit about the memory-based problem solving or question answering. And the context here, we have a knowledge base and a complex question, and the task is to find the correct model in the knowledge base that answers the question and explains the answer. So it's a model, or rather an answer can be found by chaining several models. So there are cases in which not a single model can find the answer. This is from the physics domain. The car starts from rest and reaches 28 meters per second in 2 seconds. What distance does it cover? The classical solution to such a problem is search, but the knowledge base size and complexity makes it sometimes infeasible or incomplete. So memory here is used to guide the search through all the possible models and predict what model can be used for reaching an answer. I'm not going to show you graphs, but I will say that the accuracy for our memory module was the same as exhaustive search in terms of planning and problem solving, and as good as the statistical approaches for plan recognition. But remember, our model, our episodic memory was not built specifically for the task that we created. We have a generic module that we use for this task. Same module, same representation for different tasks. In terms of scalability, retrieval was not proportional to memory size, which is what we wanted. We didn't want to get slower and slower as the size of the memory grew. We were able to speed up problem solving and maintain this multifunctional memory structure. With this, I will basically move on to some discussion points as to how we could use Watson in memory, and just to list the applications domains that, dialogue, remembering what was said, how can we detect the goal that the user has, how can we predict what he or she is going to ask next. In robotics, how do we deal with complex behaviors? How do we learn these complex behaviors? How do we learn to predict what other people will do when exhibiting such a complex behavior? And, in terms of virtual agents, again, prediction could be a big place to apply memory. This is it. I'll take questions.
Thank you, Dan. That was great. Audience, please press *1 to unmute your line to ask questions of Dan.
Hi, Dan. This is Jim Sporer. Thanks for your presentation. I do have a question on that memory as a service. When you look at things that are available, now, some people have said, like, Facebook provides some form of episodic memory for people, and there's Evernote, and I guess Twitter streams, and the various social media sorts of things. I'm just curious your take on, memory as a service, and what you would, how would you conceive of that, given the things that are out there and what you just presented? How would you conceive of memory as a service?
Yeah, I think Facebook and also Google Plus has a feature like that. Yeah, I think the application to photos, for example, right, where you could relive your, vacation in the forms of pictures you took. I think that's a very interesting application. And it relies on, the richer and richer metadata that we have for such pictures. And I think we can expand that by taking more and more context from the, basically taking more and more context about the episode, where it happened, when it happened, what other things were happening at the same time. So I think that's a great application area.
Just one quick follow-up, and I'll let others ask questions if they want. But and I'll share this on the CSIG LinkedIn discussion area that Diane always mentions at the end of these calls. But I'll post an interesting URL to that LinkedIn discussion group, because I recently found some work at, I think it's MIT, where there's people thinking about an episodic memory that's based on taking a picture of every door that you go through. So think about, in the course of your day, every door that you walk through. And there's researchers building databases of every doorway they walk through as a basis for a particular type of episodic memory, and doing various types of cognitive psychology studies around episodic memory. But I'll share that on the LinkedIn discussion group.
Thanks. Yeah, I think where I see, something that could be improved is the retrieval. So you can store things on Facebook, Evernote, Twitter, and Google+, but you have to actively go and look for things when you want to remember something. So this automatic retrieval, given a new situation, is not there yet.
Dan, thank you very much. This is Scott McLeod. I posted part of my question in the chat. I appreciate your conceptualization of human memory and as it relates to potentially episodic AI and machine-based memory. When a neuron fires in humans, that leads to that can lead to episodic memory retrieval, or to various other kinds of human memory. I'm curious whether if you had a computational model of a neuron, as I've seen in Google Brain, and I'm curious if IBM Watson is working with this, corresponding to a biological neuron, both informing memory, how would this inform your developing, conceiving of AI memory? Would a computational model of a neuron help with specific aspects of your memory model? And is this a fruitful direction for your research?
The way I approached this was at a higher level than the neuron level. I know that when neurons fire in the brain, right, there's some activation links between them, connections that get stronger or weaker based on these firings. So in a way, that's kind of the memory of their functioning. Yeah, I'll have to get back to you on that. I'll have to think whether the memory can be applied at the level of a neuron. Right now, I'm thinking kind of bigger, higher level, I would say, than the neuron.
Great, thank you. It will be fascinating when, for very, very robust AI, and specifically with memory, I guess, I think, when the correlations become very robust between, biology, cognition, and biological cognition, and, AI cognition. Thank you for a fascinating presentation and an interesting talk on memory.
Thank you.
Well, thanks, Dan. We're out of time. So thank you very much for being our presenter today. I will, as Jim said, start a discussion on our LinkedIn discussion group, and I will send you the questions that have been asked in the chat, and I encourage the rest of you to continue the discussion there. My speaker for next week had to postpone, so right now I don't have a speaker for next week. If anybody has a topic they'd like to present, please send me an email. I will send you a reminder if I line up a speaker, or I'll let you know if we don't have a call next week. But I hope we do, and I hope we all see you then, and thanks for joining.
Thank you.
Bye now.